Slides are visible, right?
Yes, sir.
Okay, anyway. So last class, we have started our this impact cratering and other things. That is essentially the geological, the ages we want to find out, for other planets. For Earth, all the geological boundaries, we have got from important events, which have changed our planet Earth. But when it goes to other planets, say like Moon, Mars, or Mercury, or other kind of thing, it is very difficult, because we don't have any idea about those things. So the only way, say, to estimate the age of a region, in Moon or Mars or whatever, the only way is through this impact cratering. Okay. So and of course, initially, this impact cratering, people were not they used to say it's not that this one volcanic crater. There was some confusions, but after a lot of missions, which went to other planets and other Saturn or Jupiter moons also, they found out impact craters everywhere. So then, this impact cratering is essentially, a basic thing in planet formation. That is how it came into picture. People accepted this one, and then the carbon, the cumulative numbers. If you plot a graphs in a region, how many we will be seeing those things also. So you can easily find out the ages actually. Okay, so these are the impact craters I showed you. Now, detection of impact craters itself is another research problem, because impact crater, if you want to detect, say, human eyes, and they used to take photographs and then they used to market this one. But we may miss some of the important craters. Some other crater would have formed and issues are there. So now people are using this deep learning, machine learning tools. Several new concepts have come up. Okay, in this crater detection algorithms. Okay, so how do we detect a crater on a particular planet given the topography map, or the images? From that we should be able to detect the number of craters. So this is a very active area of research, nowadays. Okay. So and then last class I already showed you, like, depending on how many craters are there, say, so we can find out. So if there are more number of craters, that means, that area is a ancient kind of thing. So like that, you see, so these graphs, that is log cumulative number per unit area. You count the number of craters and then you plot it, this type of a graph. So you can easily find out, you see, these are type of things where crater equilibrium, it will reach, and then you can easily find out the relative age. Basically, we will not be able to get the absolute age, but relative ages can be found out. So initially this technique was proposed, and then, on the moon, say, because human missions went, samples was brought, the carbon dating has been done, then, people got confidence in this type of techniques itself. So we will be discussing about this crater size, frequency distributions, and other things. Okay, so this also we have said. And finally, say, so we said the last class, the only way Earth means you can do whatever you like, but remote sensing data only, one has to use, to understand this crater detection. So, all other details also. So this already last class I have already covered this, the remote sensing kind of thing. And finally, say, so we have these projections, and we just set these numbers also, like, these topography images. And then, so we have given these type of things also. Okay, like the descriptions are there, like, what the people, they use these type of words to say. Mare means, it is a sea, ocean, as these are the names which regularly people use. If you see any JGR papers, they do write these type of names itself. Okay, so this what, so the crater population statistics is okay. So this has played a major role basically, okay, in the last 20 to 30 years in establishing, the planetary chronologies, okay, in determining the nature of the planetary surface process, say, and of course in inferring the characteristics of an asteroidal populations, meteoroid complex. So this has become a very important thing. Okay, so it has become a very important thing. So now these analyses, they have become a reliable tool, for probing the physical environment of the planetary surfaces and interiors also. So it has a lot of so this has become, a very large interest has come. Okay, there are several applications have come into this one. So the crater analysis, it is basically, it is very important to understand, the planetary chronologies, and to date the geological unit. That's the relative ages of all these planets and events, and then to identify the surface and subsurface processes, and then to provide a framework for interpretation, data from other fields itself. Okay, so the dating of planetary surfaces. So this was one of the major thing itself. And then the detailed analysis. So the crater frequency, like you have to count the number of craters and then their size, frequency, density, morphology, distributions. So this has been and this has been used to estimate the relative ages in all other planets itself. But the moon, the advantage was because we had already the samples which came from moon. So there was a nice calibration was done between these techniques, that is from the images, whatever you get the ages, and then you correlate with the carbon dating and others. This has been nicely been calibrated. So now this technique is is widely used to find out the relative geological age for other planet itself. So the crater analysis, so that is the only way you can say this time is to obtain this geological ages itself. So now that's what I'm saying. So for Mercury, Venus, and Mars, because there has been no human missions and no samples have been brought out to Earth, and then these ages have been found out. So the crater statistics say. So this is the only way we can do this. The geological ages itself. So that's what you see. So these, of course, the Earth also we have used, and it has been calibrated also. So, and of course, the lunar crater, the return sample ages, the impact fluxes, as all have been estimated using the crater population statistics. So this is what so the moon say. Of course, in the start, I have shown you some slide where there are large amount of craters. So this only just shows the young craters, basically, that is younger than 290 million years. And then if you count this number of regions, say, okay, people have estimated, and then if you try to find out the size, frequency, distribution, you will get different type of plots, okay, indicating the ages. If when the ages are different, say, so this type of frequency distributions also will give a different type of things itself. Okay. So this so this analysis of micro crater populations is very, very important itself. So the crater analysis, it is very important to improve the absolute dates of surfaces of all the terrestrial planets, and then we can have correlations with the geological time itself. Okay, so that's what we said. So now so this is on the far side of the moon. So there are more number of craters to say. So what is that we try to say? No. Previously I have shown you slide also, right, last class. So more number of craters to say. That means what is the relative age of this region?
Older.
Yeah, it is very old basically. Okay. So this is how we try to find out. So now these are some of the craters. Before we go into planetary things, how people identify the craters is very important. Okay. So these are some of the craters which are located on our Earth itself. So this is okay. So this is a famous crater in South Africa, which is 1.2 kilometer diameter, and people have done the carbon dating, radiometric dating has been done, and its age is some 250,000 years old is this age of this crater. Now, if you see this B-side, this is basically a Wolf Creek crater. So it's in Australia. It is 1 kilometer diameter and 1 million years old itself. And this is a famous, Arizona crater, which I have shown you last the previous classes also. And this crater is one of the, the excursion site for all the astronauts, to understand geology, the crater things, and other things also. And its age is 50,000 years old. And of course, this already I told you, the lunar crater in our India, 1.8 kilometers the diameter, and its age is some 50,000 years back or whatever the age of this crater also. And of course, NGRI, you say, lot. I have shared you those papers itself. Okay, and he's a misstated impact structure. So this also is in Canada, which has been identified as impact crater, and he is a crater in Namibia, which is in Africa itself. Then you have two craters. It's a double impact structures. This in Canada. One is a 24 kilometer, and another one is the 32 kilometers diameter age. Then we have this Goose's Bluff structures, which is in Australia. This also is a very important crater. Age is 143 million years. And then there is in Charles, one more important crater is there, like 18-kilometer diameter. Not much studies have been done for this crater itself. So now if we see the velocities of these craters, it looks something. So now the velocities of this craters is as follows. Okay. So like if we see in our Earth, people have measured this velocities itself. So what it says is in Earth, the average Earth impact velocities. So it is basically something around the average kind of thing for asteroids. It is something around 10 kilometer per second, and if the short period comets are there, say, so this goes up to 20 kilometer per second, and if it is a long period compact, impact velocities can be as high as 50 kilometers per second itself. Now on moon, it is slightly, you see, it is a 10 kilometers. So these are the velocities which people have measured it, say. And if you see in other planets, say, just 1 second. I'm sorry, other meeting was going on. Okay, voice is audible, right?
Yes, sir.
Hmm. So you can see, so this is, which slide shows, the impact velocity. Okay, so like, so for Earth, say, the average impact velocity is how much these impact craters will come. So on an average, it is something around, you can say, some 10 to like, say 15, this color is, the Earth color. So this orange one, if you see, say, so almost, some 15 or 16, something like that, you see, kilometer per second is the velocity of the impact. So moon is slightly on the lower side. So if it is a comets or something, so the impact velocities can be, 30 kilometer per second. Then if it is a long period comets, say it is something around 50 kilometer per second itself. Now if we see other planets, say, like for Mars, Earth, and then Venus also, you can see the impact velocities on Mars is something around, maybe 8 kilometer per second. Then moon is, more than some 16 kilometer per second. Then Earth is, almost, I think, 18 kilometer per second. Then Venus is much more higher. Then Mercury is much more higher. So you can see, so these are, what do you call these type of impacts, which are extremely high, say 10 kilometer per second, 15 kilometer per second, say. So what do you call these type of impacts with these velocities? Say 15 kilometer per second, say in a second it is 15 kilometers, 18 kilometer per second, say. What do you call these type of, the impact velocities? What is the word we use when these velocities are extremely high, say? So right, the speed of sound, say. Okay, things are more than speed of the sound, what happens?
Hypersonic.
So this is a hypersonic basically. Okay, so hypersonic means is extremely, the higher itself. And then when the things are hypersonic, so what happens basically?
So they
Have you, any
they
of you
create,
remember what do you mean by shock waves?
yes, so they create disturbance in air when they travel.
No, disturbance will be there. See, the hypersonic is fine, 15 kilometer per second. So, what do you mean by shock wave? Like a shock means, what is a shock wave velocity? Suppose if I take a granite, okay, or any material, say, it's a shear wave velocity. It's a shear modulus mu, and it's a density, say. So, square root of mu by rho will give you, the shear wave velocity. And then if you want a longitudinal wave velocity, so you would have studied square root of E by rho, Young's modulus, lambda plus 2 mu by rho. So that will give the velocity. So generally, if you take rocks, say, like hard rocks, the shear wave velocity will be around 3 kilometer per second. Okay, so if things are more than 3 kilometer per second, say, okay, that means the energy is moving at much faster thing than it is propagating in the medium, so it turns out to be a shock wave itself. And then here the velocities are of the order of 18 kilometer per second. So the energy is moving at so faster than it moves inside the medium itself. So this creates a lot of the shock waves and other things. It will come in our the material will be subjected to all these kinds of complications itself. So now what one does, and our this one says. So and of course one bad thing in our planet Earth, not bad thing or whatever. So one thing what happens in our planet Earth is our Earth is a dynamic planet. So because atmosphere is there, plate tectonics are there, say. So like this is the original craters if it was formed like this. Okay. So what happens is because of this the erosion, the crater maybe later on you see, or the crater would have happened in water, or in the below the ocean itself. So then eroded craters. So the erosion also happens, and finally, so you will see these entire the crater things will get slowly, destroyed basically on our planet when compared to other type of planets itself. So now what one does is, to identify whether it is a crater or not. So they use this shock metamorphism concept basically. So the rocks, whatever, I think you have heard it, right? Metamorphic rocks, basically. What do you mean by metamorphism? Yeah. In geology, you would have seen igneous rocks, metamorphism, metamorphic rocks, and sedimentary rocks will be there. Metamorphism. So this word, what does it mean? Metamorphism.
Change in the property of rocks due to high pressure and heat.
Yeah, due to high pressure. Now, in shock waves, say, so because there's a hypervelocity, hypersonic impacts, right? And you will be having huge shock waves, basically. So what happens is, the rocks, say, if you take a quartz or any rock, and if it is subjected to this type of impact, say, so impact means, huge pressure actually. And then temperature also will be extremely high. So what happens, the rock will changes its properties itself, So what happens is, so this is a famous graph, that's the shock metamorphism graph, they say, where x-axis is the pressure and y-axis is temperature basically. So during impact, say the shock, which the pressure basically, so it will be developed something like this. So near this impact region, so this red color you are showing, so this is a place where you are having the impact. So here the shock pressures will be extremely high. It is more than 500 gigapascals or something like that, and the temperatures also will be 10,000 to 20,000 degrees centigrade. Huge temperature will be there. And then once you cross this 5 regions, that is IV, so this they call as bulk rock fusion, this region. So here the shock pressures will be something around 100 gigapascal, temperature will be 5,000 degrees. Then we have another region, so the 3, so that is what is a 50 gigapascal, and the temperature will be 900. So like this it keeps on going basically. So now this 0 say, so as of course it decreases with increase in the distance itself. I think some cube or something will be there. So here as you go far away from this impact say, you will see only elastic deformation only, and slightly that is 0 what we are indicating here. Then there is a planar deformation, fractures will be there in this region where you are having shock pressure as 10 gigapascals. Then as the pressure increases, say, when it comes to this impact region, so you will have these type of things itself. Because of a huge pressure and temperature, the initial rocks, say, whatever rock you are seeing, it changes its, you will see a different type of rocks itself. So that's what this is, stages, elastic deformation far away from the impact, then planar deformation features. Then you will see in that second region, so that is in this region, you will see this type of diaplectic silicate glass are melting, because temperature is also very high. And this region 3, say, you will see feldspar fusion. Then in the region 4, bulk rock fusion. Then 5 here, because the temperatures are extremely high, say, the impactor may even melt also, and become a vaporization, you see, it just evaporates also. So this also is a possible. So now this is a very important graph which shows the shock metamorphism. So this is normal crustal metamorphism is, so this type of changes you will see below the earth actually, like in the mantle region, or as you go to inner core or outer core or whatever. So there also will be having a huge pressure and temperature. So in this temperature you will see different type of rocks. But in shocks, say, because the pressures are extremely high and the temperatures are also extremely high. So what happens is, when 100 gigapascal, the same figure I'm showing, vaporization, melting, you will see this type of diaplectic glass. So you will see this type of schistosite, white, So these are special rocks basically. That is a quartz, it automatically gets converted into different type of rocks itself. And this is what they call as shatter cones also. So these type of the rocks, and if you find in that region, so that means they would have been created by impact itself. So using these things is so people detect whether it is formed due to impact crater or not. So these are very widely used the results itself. So the same thing only the shock metamorphism I am showing. Suppose this is a general thing which I am showing. So the high pressures are there and here's a temperature. So you will see the shock metamorphism. Suppose if it is a quartzite that's converted into schistosite or something. Suppose if there is a graphite cell. Now what happens? The impact happens on graphite cell. So due to this huge pressures and then the temperatures. So what happens to graphite? Now, can you see this graph? What happens to graphite? Graphite automatically converts into
diamond.
So it automatically converts into diamonds. So if the impacts, if it happens on graphite, you will see diamonds because diamonds are created due to high pressure and then you see the high temperatures itself. So the rock's properties, the type of rock, everything, it changes because of the shock and then, the high temperature itself. So this is the one, people use to identify the impact craters. So this is a regional. So this is what generally, happens inside the earth actually. And this is what happens in shock metamorphism. So generally, where do you see this type of shock metamorphism? Where do you see these type of, the features? No. Inside earth or outside the earth? Where these impacts happen? So the shock metamorphism, where
outside Earth.
That is on the surface itself. Okay. So generally, if you see diamonds, where do they form? They form inside the earth actually, and during volcanoes or something, they come out. But when there is a shock metamorphism, say, and if it happens in graphite because of the high pressure and then temperature, so automatically, you can see a diamonds which can form on the surface itself. Okay, so this also you can see the shock metamorphism on the surface or the near surface regions itself, and the pressures also say is almost 100 to 400 gigapascals. So the entire rocks they change their structure and other things also it happens. Now temperatures is 10,000 degrees centigrade will be there when this impact happens, and the projectile or whatever the materials it just vaporizes basically. And then the strain rates will be, you can see, extremely high, 10 to the power of 6 to 10 to the power of 7 per second. And whereas if you see in the strain rates in ordinary the slow geological processes 10 to the power of -3 will be there, but it's a huge the strain rates. And then time for completion say, now generally if you want to have these type of diamonds or system to form inside earth, it takes large amount of time. But during impact say these things forms instantaneously, these things forms also. And then reaction times also rapid, and then these are during the impacts itself. So then this is what it says. So now when approximate pressure is like this is say, okay, and then estimated for the temperature and pressure, what happens basically? So if you see ordinary rocks say, okay, that is a non-porous rocks itself, when the top to pressure is 2 to 6 gigapascals and the temperature is less than 100, so you will see rock fractures, and then these fracturing is a breccia formation. They say shatter cones will form, and as the pressure increases, temperature also remains constant. So you will see mineral fracturing, basal basal twins. So these type of features you can observe in the field itself. Now, as the pressure increases, temperature also slightly increases, you will see quartz with PDF. PDF means a planar deformation features itself. And then this quartzites, quartz, it automatically converts into schistosite kind of mineral, and graphite it automatically converts into diamond when it is subjected to this much pressure and at this much temperature itself. And of course, as the pressure increases, so you will see this type of another soisite, this material also forms on the surface itself. And of course, as pressure still increases, as you go towards the melting, that is near the impact thing itself, and the temperature also will be high. You will see this type of rock glasses, because everything gets melted and then condensation happens. So you will see rock glasses, diaplectic quartz, these type of things you can see in the the impact region itself. So these things you can observe easily in this one. So the same thing I'm showing here. If the pressure is less than 2 gigapascals, say fracturing, brecciation, you will see unique shock features you can observe. and 2 to 30 say shatter cones will be there. Then 8 to 25 say microscopic, the PDF, that's the planar deformation features you can see, and 25 to 40 say amorphous faces, that is diaplectic glasses and other things will come. Then 35 to 60 say melting happens, feldspars, these kind of things will get formed. And 60 to 100 say all minerals will superheated rock melt kind of thing happens, and more than 100 gigapascals everything vaporizes. Basically you will see nothing, that the whole thing gets vaporizes and disappears into the atmosphere. So these are some of the things, like you can see right here AB, you can see these type of planar fractures you can see. So these things, at the impact sites you will find these type of things in quartz, granites if you see say. And then this is a feather features they say. So this also happens, so this has been observed in an impact structure in Canada. Then you can see, so these are all planar deformation features. So this is a quartz crystal, in Sweden, something they have observed. And then this is experimental they have done, like basically. Okay, so this you can see these type of features you will see in a region say. So when you see these type of things, so that means these things have been created due to impacts itself. And this is what they call, and of course these are planar deformation features are there, and these you can see the beautiful, the nice things you can see. So these are what they call as the shatter cones. Can you see here the cone kind of formations? You can see these also a shatter cone. So these type of things gets formed actually. The same quartz itself, it gets converted into these type of different this type of rocks due to high pressure and then high temperature itself. So when you see, if you find out shatter cones in that area say, so of course shatter cone, these type of things also gets formed due to volcanic thing also, but impacts things also will create these type of issues. So you have to correlate basically. Okay, so these are some of the shatter cone formations actually. Okay, so this is a river, you can see a huge shatter cones are there. You can see the rocks here, these type of rocks here also, this lady is sitting right. So this is what the shatter cones they say. So when you see these type of formations, that means the impacts have been made at this place itself. So if you want to see a lunar crater in India, if you go to these places, if you identify these things, then you can classify it to be an impact crater itself. So this is what they call as a PDF, the planar deformation features. So these things will form, maybe at low pressure and at low temperature. So this is a quartz. You can see all the cracks are there, right? So many, the cracks, small deformations you can see here. So when you see these type of formations, so they indicate some type of impact in that place itself. So this is how people, what they do is the geological expeditions they go. So once they identify a crater say, so then they go to that place, and then you have to identify all the rocks, whatever the rocks are there, and then you have to search for shatter cones, you have to search for planar deformation features, the ejecta and other things, so used on that one side, then you can estimate whether this has been created due to impact or not actually. Okay, so this is how they do in our earth itself. And of course you can't do this on other planets. Of course moon, human missions have gone, they have done some carbon dating or whatever, but other planets you have to go only through remote sensing kind of things. So if you see the morphology say, so of course based on the impact craters observed on earth as well as the moon, so the this crater morphology, this subject has evolved nicely. Okay, so the fresh impact craters say. So when you see this type of fresh things you can see in moon or other planets, they can be grossly characterized, circular rimmed depression kind of, like a bowl kind of a thing. I will show you photographs also that like this one. Now, although this description can be applied to all craters, say, independent of size, of course, if you see moon, you would have seen the topographic map, variety, size, age will be different, substrate material, planet, it depends on the gravity of the planet also. If the gravity is so high, say, then you will see different type of a crater. If the gravity is so low, so then you will see a different type of craters itself. So a lot of craters have been observed on moon itself, like the rocks, whatever they have made brought from moon, say, that also has small craters, basically micro craters. There's a 0.1 micro, this one, and of course a 2,000 kilometer diameter basin is there in Hellas Basin on Mars, and then I will show you some more figures. I think 4,000 kilometer huge crater basins have been formed on other planets itself. So morphological features, so the increasing size has been established. Of course, exceptions and other things are thing itself. So basically, all the craters, whatever you see on other planets or even on Earth also, you can classify them into some 4 or 5 classifications. One is a simple crater. complex crater. Then we have multi-ring basins also, impact basins also we say. Then we have aberrant crater types basically. So these are the broad classification of impact craters itself. So now what are the major portions of a crater? How do we describe a crater itself? So each crater say, we use these type of words, floor basically, okay? The floor means, the bottom of a crater say, either a bowl shaped or flat, usually below the level of the surrounding ground. So this we call as a floor itself. So you can see here, so this portion say, so we call this as a floor actual. So this is how we describe the craters. So when they say floor say, so this means this region is what they call as the floor of a crater itself. Then we have central peaks also. So we will come to this one, walls say. So the interior sides of a crater usually steep basically. So they may have giant stair-like terraces that are created by slumping of the walls due to gravity. So this they call as the walls of a crater. This is a very simple crater basically. Okay, so you can see this is what they call as the walls of a crater itself. And then so this is what they call as a wall. Then this word used is rim basically. So the rim is nothing but the edge of the crater, and it is elevated above the surrounding terrain because it is composed of material pushed up at the edge during the excavation. So this we call as the rim of the crater. So you can see this is what they call as rim of the crater. Okay, and it's a generally if you see any crater say, so it will be slightly elevated basically. The floor will be less than the ground elevation. The rim will be slightly more than our ground elevation itself. So this we call as a rim. Then this is what we call as inside the floor, and this is what we call as the wall itself. And then ejecta also. So now when during a impact, say some material, it just flies off actually. I will show you why it happens also during an impact event. So this day we call this as ejecta also. And it is distributed outwards as from the crater's rim onto the planet's surface as debris basically. So it is basically some rock, it just flies off because it's a hypersonic velocity, right? Because of the shock waves and other things also, compression tension kind of a thing. I will show you at a later stage. So the loose materials which is in this region, so the materials which was located in this region, because of the impact, it just flies off actually. Okay, and you will see these type of rays, it just gets deposited outside the region. So this portion, so we call this as ejectas also. Okay, so these are terminology we use. Then rays also we use, the bright streaks say, okay, extending away from some type of great distances, composed of ejecta material. So this we call this as rays. So this is I think a typical crater in Mercury. So the rays are bright also, I told you last class, that means it's a young crater or something like that. So these rays say, all the ejectas basically, that is a material which flies off from this region. So it follows this type of paths basically. Okay, so this we call as rays itself. And then some craters, the complex craters will be there. You will see the central peaks also. So you will see a peak which forms in the central area of the floors of a large craters itself. So this happens in very large, the craters itself. So that you will see in the center, so you will see elevated region. Only you will see this type complex crater. So this we call this as the central peak. These words are used. So how do we describe a crater? So if you see any crater on moon, say, so the words what people use is the floor basically, or what is the floor depth. Okay, the depth of the floor, and then the crater diameter of the rim of the crater basis. So rim means the outside edge itself, which is slightly elevated compared to the neighboring region itself. The ejecta, the material which has flied off from the inside the crater, how much distance it has fallen. The ejecta blankets or whatever, they use these type of words. The walls of the crater, and then the central uplift say, okay, that's what the central peak or whatever the words are used. And then you see the rays basically, that is the ejecta rays, how they got deposited in all these directions. So all these type of words are used to describe this craters itself. So this is the same thing. So this is a simple crater. Okay, the same crater. If you see a simple crater, how it is described? If you can see, so this is a crater which has formed due to an impact. So this is the rim basically. So initially the crater was like this. Okay, this was a ground elevation. The floor is so this is the floor of the crater or whatever. So this happens when it has created an impact. So that this is a rim basically. You can see here. So this DA, we call this as apparent diameter of the this one. And this is what it has happened. So now if you see craters, it looks like this. So this region, you will see the highly shocked breccia with melt fragments, because here the pressures are too high, and then even the temperatures are also too high during the impact. Okay, and then you can see, so this is the region where this breccia without melt fragments also in the region will be there, and these are the shocked target rocks actually. and these are all the fractured and brecciated target rocks. You can see these type of features also. And if you drill in a crater, say, you will find out all these features itself. So we use this type of terminology. DA means the apparent diameter of the crater, and then DA is apparent depth basically. So from here to here, so this we call as apparent depth, and then DT, say, that's the true depth basically. So the true depth was from here to here itself. So what happens, the crater basically, the projectile has come up to this place. So I will show you that animation also. Then slowly what happens, after some point of a time, the materials which goes away, it automatically, due to gravity, so the crater collapses, and then this material gets deposited inside the crater itself. So DT, that's the true depth, means from here to here, that's a melted the segment or whatever we have. Okay. So these are the words we use to describe the craters itself. And of course, this is a complex crater means so once the crater happens, say, so the central portion also, it just it rebounds back basically, and you will see this type of a peak in the crater itself, and then you will see the these huge walls, say, they collapse basically due to gravity or whatever. So this is how a complex crater looks something like this. And here I think the marker they have even given, like where the these dielectric glasses gets formed, and where do you see these shatter cones also. So shatter cones, you can see the lower limit is here basically. Okay, so you will see the shatter cones. If you drill, say, you will get all these type of materials itself. And here also we use these type of words. So DA is the apparent crater diameter after collapse of the transient activity. Then this is the diameter of the central peak, the region itself. So this is how we define, how we talk about the crater. So we will be using these type of words: so floor, wall, rim of a crater, ejecta, that is a material which is thrown out of the crater. Then the rays, the in which direction, the ejecta rays basically, ejecta blankets, then the central peak. So these are the words which we will be using to describe our craters itself. Okay. And these are the words we will be using, like apparent diameter, apparent depth, true depth of a crater, so they use these type of terminology to describe our craters itself. Now coming to the simple craters, it is very easy to understand. So the simple crater is just elegant bowl type crater. This is, I think, a crater on Moon, and this is a crater on Mercury. I think very simple crater which has formed on these planets. So you can see, so this type of craters is common, okay, and it is less than 15 kilometers diameters on Moon, and 3 to 6 kilometers on Earth itself, depending on the substrate rock type. Okay, so on Moon up to 15 kilometers diameters also, you will see this type of simple craters. You can measure, and this interior of the simple crater, say, it has basically a smoothing, a parabolic profile basically. Okay, so a simple parabolic kind of a thing it will be having, and it's a rim to floor depth actually. Okay, so rim to floor depth, that is a rim diameter. So from here to here is a rim diameter, that apparent diameter we discussed here. So this is a floor depth, say, people have measured, they have done simulations from the geological things. So they say that it is about 1/5 times of its rim to rim diameter. So the depth of the crater, the rim to floor depth basically. Okay, so that means DT, the rim to floor depth. So this are DA. So this DA, say, when you compare with the capital DA, say, so this the ratio is almost 1/5 times. So if this DA is some 100 kilometers, say, what will be small DA? No. So if it is 100 kilometers is the diameter of the crater, say. So the floor depth will be how much? No. So what is that? This thumb rule says no.
20 kilometers.
20 kilometers is a depth. So this is a geologically people have observed on Moon as well as Earth, and of course I will show you some numerical simulations also. And then material, Arizona crater, say, you can check with the lunar crater, Arizona crater, and other things also. And of course on Earth the only problem is erosion happens basically. You will not get the exact things itself. And the floor of the simple crater, say, is underlined by lens of broken rock basically. So this is what they call as a broken rock. Here you can see in this region. Okay, so this they call as a Bracia, the lens or whatever you see, this region itself. So you will see this type of Bracia lens. So these are the terminology they use in to describe them in the geological things itself. So which slid down the inner walls of the crater shortly following the excavation. So originally the crater was like this. DT was the depth basically. So now after the crater has formed, then due to gravity, so the crater collapse, all the material will come to the center basically. Okay, so this portion they call this as the Bracia lens or whatever this one. So all the simple craters you say. So you will see Bracia lens in the at the center this itself. Then this Bracia, of course, it includes a representative from all formations intersected by crater, and may contain, say, horizons of melted or highly shocked rock properties itself. And the thickness of this Bracia lenses is typically half to 1/3 of the rim to floor depth itself. So the rim to floor depth is same. Okay, so that is dA versus dt. So this whatever you see dA or whatever say, so it will be something 1/3, 3 times or half of this rim to floor depth. You will see these type of features. So these are just empirical kind of numbers after studying lot of craters. These are just thumb rules people use to find out how much will be the depth of the thickness of the Bracia lens, and then the floor to depth itself. So this is what is the crater formation. Okay, these are the variety of steps. So you will see. So this is impact, which is happening. Of course, this is not 90 degrees impact. It is inclined impact basically. Okay. So now once this has been impacted, and its velocity is 20 kilometer per second. It's a hypersonic velocity. Okay. So once it has impacted this feature, so you can see here. This is initial stratigraphy. So the top layer consists of limestone, then we have a sandstone, and then we have this gneiss actual. So you can see the stratigraphy also. So gneiss is the oldest rock. Then we have studied, right, principles of stratigraphy. So this is younger kind of things happens here. So now once impact happens, say, so this is a stage B. Okay, immediately after contact with the target surface, the projectiles, the impact penetrates the target volume, and the shock wave develops because velocity is 20 kilometer per second. So it penetrates. It is like a faster than a bullet itself. It penetrates the material itself, and then you will see a shock wave here. So a jet of tektites is there. So these are also, tektite is also, the highly shocked rocks itself is ejected from the horizon just below the target surface. So now after this CSA, that is this type of 60 milliseconds after impact here, the crater starts excavating here itself. The crater formation has begun in earnest, and the subsurface targets is becoming subject to radially attenuated shock pressure and temperature conditions. So here the temperatures will be 10,000 degrees centigrade, and the rocks also start melting here, and the shock waves are also, pressure is also huge actually when the near the impact itself. And you can see here, so this is what they call as the ejecta actual. Okay, the material is just trying to fly off from the center itself, and because the temperature is extremely so high, so this yellow color thing, if you see this asteroid, it just melts away 10,000 degrees centigrade, and the rocks whichever is in contact with this one, so everything vaporizes, or it starts melting away itself. And after 10 seconds, say, a deep transient crater has been established. So the crater has formed, and the whole material, say the asteroid or something, it has just evaporated basically. Okay, it has just vaporized because of high temperature and then the high pressure itself, and of course the nearby rock or whatever. So you will see these type of plumes basically. Ejecta cloud or vapor plume has risen. You can see there is no yellow color itself. The whole asteroid itself has evaporated basically because of high temperature and then high pressure itself. And then of course the shock waves gets formed, so they travel inside this medium itself. And you can see, so this is our transient crater, they say. Okay, so this is how the original crater. So this crater has formed in D, and then you can see this ejecta, so the material. So this they call as ejecta terrain also. Okay, so the materials, it starts flying off just after 10 seconds. This itself, and then and then once it has this crater, say after 10 seconds it has formed, then it is almost 1 minute actually. So what happens is a transient crater, so it just collapses because of the gravity. Material flows inward. So now this starts collapsing. The materials, it flows automatically to the inside itself because gravity, right? Everything has to come to the center itself. So the material just comes to the surface itself. Material flow is inward, directed from the edge of the crater and upward in the inner sector also. Now in here, why this is happening? So in the central uplift, say, what is the reason for this central uplift? You can see here the central uplift, basically the whole thing, it just lifts up actually basically. Now can you identify the shock waves? A shock means what type of waves are there? Shock means initially what type of things will be there during impact in this nearby rock. They will be subjected to what type of waves actually, or what type of the stress mechanisms will be here. What type of stresses will be there at the impact place? See, what type of stresses in mechanics you have studied, right? Shear stress, tensile stress, compressive stress actually. So what type of stresses will be there in this region? No. When impact happens?
Compressive stress.
Yeah, compressive stress only. Okay. So, and of course, you will see compressive waves also. Now, these are like seismic waves only. So, this is and it's the shock waves. These are compressive waves. They start propagating in the rock itself. Now, when there are a lot of geological layers are there, so what happens? See, when a wave encounters any, discontinuity or any geological layers, so what happens? When a wave goes away, you would have studied, right? Reflection, refraction, those things happens. So what happens when the wave reflects back, say? So what happens? Your compressive wave, it is hitting a boundary basically, okay, and it reflects back. So what type of waves gets generated? Compression converts into no. See, a compressive wave is hitting a layer basically, okay, it is hitting a boundary. So then what happens? What gets reflected back? Some portion will get transferred. The compressive wave still propagates into the other layer, but some portion gets reflected. So this reflection creates what type of waves? No. See what type of waves will get generated, See, a wave is hitting as a compressive wave. So when it reflects back, so what wave will come?
Expansion.
No, tension basically. Okay. So what happens? Tension waves also happens. So when tension means what will be there? Compression will be like this in this direction. Okay, inside the rocks. But when tension comes, so all the material goes in the upward direction because of the tensile wave itself. So that is the reason why the central uplift is saying. You will see these type of things itself. So the material first, everything goes into the earth. Then once again, once the shock wave has propagated and the shock waves, they get reflected back also. So then automatically tensile things comes up and some of the materials, it gets uplifted also. And because at the center, the most compression will be there, so because of reflections, you will see tensile waves also. So the material, it comes back and because the shock wave velocity is very high, say, so some of this material, it just flies away actually. Okay, that's what we are calling as ejectas and other things also. Okay, so this portion comes up. So that is what we call as that is a transient crater has collapsed and material flow is inward directed from the edge of the crater and upward in the inner sector because the compressive waves, reflects back and then converts into a tension kind of a thing. And then the vapor cloud also, so it also begins to collapse while the ejecta curtain. So this is what we are calling this as ejecta curtain. You can see this ejecta curtain still, it is going, you followed it, the material is still flying up. Okay, central uplift gets formed. And after a few minutes, it's like after 10 minutes basically, okay, after the impact has happened, the impact crater is essentially completed itself. So you can see the this melted material, the vapor cloud or something, it may get this one, so they may get deposited here. There is a melted kind of things, and then this happens here, and you can see what has happened here. Now you see this one. So if you compare the original stratigraphy, say, and this new stratigraphy, see what has happened to the stratigraphy now. Initially, we had a limestone, then sandstone, then granite used to happen. And now what has happened? Now, what has happened to the stratigraphy? Now, the original stratigraphy, what has happened now? See, do you see any limestone or sandstone here? No.
Completely changed.
Completely changed. Now, what has happened? See, when you go as per stratigraphy, see with the Stenos laws or whatever you have studied. So, what we have studied was the oldest will be at the bottom, then younger, the youngest kind of thing we had. But when the impact craters, what happens is the oldest material also comes up basically. You followed. So the oldest rocks also comes up and then ejecta, they may get deposited on top of the limestone itself. So the topmost rock will be granite and below you will have a limestone. So if you go to as per Stenos laws of stratigraphy, say, if you don't know that it is a impact crater, the topmost is the youngest. You see those rules also, we will have a problem basically when we are having a impact crater itself. So this is how the crater gets formed. These are the various stages basically how a crater gets formed. So the same thing I am showing you here also how this the impact crater. So the impact starts, the shock waves. So once the material comes up, say, then automatically because of high temperature and high, this automatically vaporizes, and then the shock waves happen. the compressive waves goes. Now, when you are having a geological layers, say, so what happens? This compressive wave it encounters, and then you will see a rarefaction, reflection, and other things also. So these waves gets converted into a tensile wave itself. So when tension comes, this ejecta starts coming out. So the whole material, it is coming out of the crater and then flying in all the directions itself. And then once this transient crater has formed, say, so you will see this fracture system. So how much distance you will see these type of cracks, these type of fractures. So how much distance we will see these type of fractures? So how do we estimate basically? These fractures, how much distance? So for that, what information we require?
Velocity.
No, velocity is fine. But how do you find out how much distance fracture goes or whatever this one say? We have said, right? The most important thing is this graph actually. So this is what we call a shock metamorphism. You can see here, these are the stages basically. So now when a crater, if you once you find out, so you have to get the pressure contours. So whenever there is an impact, say, if you can numerically simulate it and if you can get the pressure contours, so based on the pressures, say, we can find out easily how much distance you can see the these type of rocks and the breccia or whatever this one. So this is based on the shock metamorphism, say, we can easily estimate actually how much distance you will see what type of material, like for example where diamonds will get formed, say. So for diamond to get formed, as already we told you, right? So what should be the pressure? So where do you see a diamond? So you can see approximate pressure should be 13 gigapascals and the temperature should be, you see, 150 degrees centigrade. So where do you see a diamond? No. So in this graphs, say, where do you see the where diamonds will occur? No. So diamond means pressure should be 13 gigapascals, so temperature should be 150, 13 and 150. So where you will see the diamonds. Which region you will see 0, 1 or 2, 3, 4 or 5. If the material is graphite, where do you see? Which region? Say for
in 1 and 2.
In 1 and 2. So this is how you can find out. So you have gone to your places and you have done the excavations, and if you find these type of things means you can easily find out. So if you are looking at if you get a diamond at the certain depth, say, you can easily work out back and you can solve the inverse problem. Okay, the pressure was this much and then temperature was this much, and you can easily estimate the crater dimension and you can construct the entire geological history of the region itself. If it is a graphite, you will get a diamond. If it is a quartz cell, you will get this type of cystovite or something. You will see that I showed you, right? These shatter cones or whatever, these type of special type of materials itself. Okay. So this is how the crater, it forms basically. And finally, once everything goes away, so you will see this type of ejecta blanket. That is a material from the here. It is just flying off because of the compressive wave due to rare fractions. It is converted into a tension wave, say, and due to tension everything just flies off. You will see this type of ejecta blanket itself. So the crater also here, you will see a central peak because of that rare fraction and others, it comes back basically. Okay. And you will see the ejecta blanket here and the vapor clouds, say, because of high temperature you may see some melted kind of fragments itself. Okay. So, and of course, people have done some simulations and geological things they have done. So the crater depth versus crater diameter, say, already I showed you, right? How much is the crater diameter to crater depth? So like I already told you, rim to rim diameter and then rim to floor depth. This is about 1/5. That is essentially 0.2. Okay. So this is the same thing. This, if you plot a graph, say, on the moon, and then you see do some kind of experiments, you can see the crater depth versus diameter is approximately 0.23 times of the crater diameter. That's of course 1/5 can be very nicely used for this things itself. I will just show one numerical simulations. They are available in net also. You can just just 1 second. You are able to see this one. You are able to see, right? This video simulations of impact cratering process.
Yes, sir.
So now this is a Lunar and Planetary Institute. They have a nice website. It is okay. So they have simulated from smooth particle hydrodynamics. The numerical simulations they have done. So these are some videos they have done. So this is a simple crater, say. So this is on Moon, and the impactor material is dunite actually. So this is a material which is in meteorites, that asteroids, and its density is a 3,300 kg per meter cube. Okay, and the diameter of this impactor is 100 meters. That is the size of this material, and impact velocity is 15 kilometer per second itself. And the gravity say of Moon is 1.61 meter per second square. And the target material is lunar crust. Okay, that is a 2,700 kg per meter cube. So if it impact happens, say, so how things like that. You are able to see, right, this one. You are able to see, right, this video.
Yes, sir.
So you can see how a crater forms. Okay. Let me just go to the starting. So you can see how the crater is forming. So this is what they call as ejecta terrain actually. Okay. So you can see the crater has already formed. Okay, in this portion of 25 seconds or whatever. So this ejecta is still flying. 34 seconds, 35 seconds, and it goes away. And you see the center portion. Say what is happening here. Now, in the center portion, if you see what is happening in this region. You can see what is happening here. See now 2.5 second it has happened, 7.5 second, 8 second, this one happened. Okay, so by this 17 seconds or whatever, 10 seconds or whatever, the crater has already formed. So this is what we are calling it as transient crater or something like that. Okay, now the only thing is you can see this crater is formed here itself, but still the material is flying off and others. So after some point of a time, so gravity comes into picture. So the material comes back to the center, that Bracia or whatever I told you, right? So everything comes back to the center, and this is how a simple crater say it forms, on Moon. Okay, so this is a nice simulation. You see, they have done using this smooth particle hydrodynamics. Okay, the ICL or whatever they say. Okay, and then they have also done like altering the impactor sizes. So the same details they have taken. Now the impactor diameter is 200 meters. So previously it was 100 meter and is a 200 meter also. You can see this video also. Is it visible, right? Now you are able to see, no?
Yes, sir.
Now one is 100 diameter. This is a 200. So left side is a 200 diameter. This is a 100 diameter. Everything is same. Velocity is same. Everything is same. But only thing is, the impactor size is different itself. You can see how, the crater depth you followed with the impactor thing, how it varies. Now, you can see how the crater is getting formed, and slowly you will see, the crater collapses due to gravity, how the breccia and other things also forms. And the ejecta material, you see, it gets deposited here, and as well as for 200 meters, say. So now you see nicely, it gets formed. And you can see the 200-meter thing. If you see the, you can see in the center what is happening. See, 100-meter thing, it was very simple. But 200-meter, what is that you are observing here? Can you see, right?
Central peak.
Center, not only center peak, the material, you see, from the rings, what is happening? All the material is getting.
So due to gravity.
It is coming to the center. You followed. So this, because of the gravity, so it comes up, and then in the center portion, you can see, because of this one, you will see this type of a small peak or something, which happens at the center itself. So these are some nice two-dimensional simulations, they have done. And of course, that code is also available, that Fortran code for ISAIL, so you can try. Okay. So these 100-meter, 200-meter diameter. Then you see this is also altering impactor velocity. One is slow velocity, what happens, 10 kilometer per second, what happens, instead of 15 kilometer per second, say, what happens on Moon essentially. Okay. So this also, I think one is 15 kilometer, other one is 10 kilometer per second. So this is, I think, 15 kilometer. This may be 10 kilometer per second. Okay, when the impact velocity is so fast, say. Now, so now you can make some observations here also. Now, now you can observe, you see. So what is the difference between if it is a high velocity and if it is a low velocity, say, what happens actually? You will see central peaks in some cases you may not see, some cases, you know, you will see variety of features itself. The rim, the diameter also, then you can measure, that is a diameter to the floor depth and all other things. If you measure, say, you can easily get, you know, some type of equations also. Okay, so this is a very, you know, they have done very nicely with a varying variety of, you know, like something. This also, I think, impact velocity is 35 kilometer per second. It's a huge, you know, velocity. Okay. So one is a 10, other one is, I think, 35. You know, almost they have increased the velocity also. So this is a huge fallout, right? The velocity is extremely high, 5 kilometer per second. So material, you see, just flies off, you know, and the crater size also, if you see, it is a huge, you know, the crater gets formed here. And the whole thing, if you see, everything is, you know, finishing off in just 1 minute or, you know, something like that, because these are very high, you know, impact velocities. So now, you know, we can make our observations also. Okay, so they have done so many things. I suggest you, all of you, to go to these websites to understand, you know, the crater depth, when you will see a complex crater, when you will see this one. So like this is, you know, impacted density. So previously the impacted density was a 3,300. Now it is, you know, 7,800. Now what happens, you know, the density, and they have fitted some type of equations also. Okay, so these are some very interesting things you can see. Now we will come back to our PPT. PPT is visible, right?
Yes.
So this is how, you know, they have done, like the numerical simulations also are there. So these are some empirical relations, like, you know, what's the diameter versus a crater depth, say, how these things comes into picture. Okay, now the next comes is a complex crater. So simple craters are very easy to understand. They don't have any, you know, complicated features. But now when do we see the complex craters are getting formed? If you see the previous videos, say, now what did we observe basically? Yeah. So when you will see these type of complex crater, complex means, you know, you will see in the, at the middle, say, some type of, you know, a central peak will be there. You know, several, the crater is not that simple. So like not this type of thing, like a beautiful, you know, simple, like a bowl kind of a thing. You will see other kind of features also. Like this is a one typical crater, say, I don't know, it's a Copernicus crater or whatever. You will see several rings, you know, you will not see a perfect rim kind of a thing. You will see several, you know, the branches kind of thing. I showed you like this type of thing. So you will see here also, like, you know, the things are getting formed. You will see several faults also here. So this is what we call as a, in the complex crater, and you will see a, you know, the peak at the middle also. So this is what we are calling as, you know, the complex craters. Okay, so the lunar, so lunar, so when do we see these type of craters? Like in the previous videos, when you will see a complex crater,
Large diameter and high impact velocity.
now large diameter, why large diameter forms, you know? See, why why the crater size is large? Because your impactor size is, with that videos I showed you, right? 100 meter versus 200 meters, say. So if it's a 100-meter crater, you will see a simple one. But if the impactor size is large, say, then you will see, you know, a huge size of the crater itself. Okay. So when the impactor size is large, then if the velocity is also large, then you will see these type of complex, you know, the features itself. So that's what they say, 20-kilometer size. And terrestrial craters. Terrestrial means on Earth. Of course, Moon is also terrestrial, they say, like Venus and Mercury, Mars, and other things also. Larger than about 3 kilometers. They have terraced walls, central peaks, and at larger sizes, and they have flat interior floors or internal rings instead of central peaks itself. So this they call as, you know, the complex craters. So these craters are believed to have formed by collapse of an initially bowl-shaped transient crater. So everything initially, everything will be simple only. But after slowly, you have seen the videos also, after some point of like 10 seconds or 15 seconds, say, gravity comes into picture, and then material comes into the center, and then because of ejecta, that complicated thing, automatically you will see these type of complex crater sets. And then the shock waves also, due to refraction or whatever, so they get converted into tension. So all these things create these type of complex craters. So now these are transitions between simple and complex craters. This has been observed, the moon, Mars, and other planets itself. And then consistent that complex craters, they form by collapse. Initially everything will be simple, but since the crater collapses because of gravity and other things, you will see these type of complex craters also. And then when you see the floors of the complex crater, that is inside the floor, they are covered by melted, highly shocked debris. Okay, the melting things, that vapor also I showed you, and melt pools are sometimes seen in depressions in the surrounding ejecta blanket also. So the surfaces of the terrace blocks tilt outward in the crater walls, melt pools. They are also common in the depressions that formed itself. Okay, and there are some people have estimated the empirical equations also. Like for example, say terrestrial structural uplift, say H of SU, final crater diameter, some type of equations also are there. Like on the moon's depth of complex craters, they increase from 3 kilometer to 6 kilometer. Crater diameters, say 20 to 400 kilometer. You may have a huge crater, but the depth may be 6 kilometer itself. And rim height, say, this also increases rather slowly with increasing diameter, because much of the original rim, of course, it slides into the crater bowl as the wall collapses also. Then complex craters, they are considerably larger than the transient crater, which so initially everything is simple bowl kind of a thing, but then because of gravity collapses, so automatically it will become a complicated kind of thing itself. So there are some empirical relations are there, how to find out the diameter, rim to rim diameters of a complex crater. It is 1.17 times dt. Dt is a diameter of the simple to complex, dsc is a simple to complex transition, and then your dt say is the transient crater diameter itself. Okay, this is how this forms, and this is how a complex crater looks like. So initially the crater will be like this. Okay, this is a transient crater. You can see this is a dotted line here. So this is a crater which has been formed due to impact. Now once this crater has formed, so that is after 5 seconds or 10 seconds, immediately the material comes into the center, and then this shock waves compression comes into tension kind of a thing. So material, you will see this type of a central uplift, and then everything flies off. And then, as already I told you, 10,000 degrees, everything gets evaporated, and then you will see these type of melt pools also. And this is all the Bracia Lens and other things forms. And then even the rim, say, which was originally here, the rim also collapses basically. And then you will see these type of faults which may form on the crater, the walls itself. So this is how a complex crater looks like. Okay, and multi-ring basins also. And of course, if you go back to that videos, you will see a complex crater, how it forms. The videos are there. I will show you, at a later stage also, and in the next class maybe. And then you also will be having this multi-ring basins itself. Okay, like this is a Oriental Basin. Okay, which is a very famous thing in moon. 930 kilometers is the diameter of this Oriental Basin. And then this is a huge diameter, 4,000 kilometer Valhalla Basin. You followed. So this is found on Jupiter's satellite Callisto. It's a huge basin, multi-ring basin, which is there on this, the Jupiter's moon, okay, satellite itself. So this is how our Oriental Basin looks like. You can see in our topography map and other things also. There are several rings can be identified basically, okay, from the topography maps, and people have made. So this region, say, okay, so this region, what they call as mare. What do you mean by mare? Now, mare, I told you, right? Our geological notation. What do you mean by mare? Mare Imbrium, mare Oriental. Then why do they use this word mare? Mare means no. So I told you, right? Our terminology. Mare means now. What is our terminology? Last class I showed you, right? Our terminology. Mare means you remember. Last
Sea
class I.
plane.
So here we have said mare means you can say sea, large circular plane basically. Okay, large expanses of dark materials start to, of course, this is on Titan, but this is basically a sea that may be due to lava or whatever on the moon itself. Okay, it's basically a sea. So this is in the Mare Oriental, they say. So that means in the inside regions, some lava flows or whatever has been happened here. So the Mare Oriental. Then this is the first ring, inner scarp, they say, 320 kilometer, this inner scarp. Then they have inner Rook ring base. Then outer Rook ring is there. Then Cordillera ring. So you can see a chain of mountains, basically. All these ring sites. So this is what they call as multi-ring basins, basically. And then the same Oriental basins, they have done the geological, because the data and other things they have used. So now here near the portions, that is a Mare which we are calling, that is a 6 actually. If you see the mantle set, so this impact, I think, it went up to the mantle or whatever. So from the mantle, so the lava has come up and it has filled the center portion of this Oriental basin. So that's what we are calling as Mare, that is a lava flow which has happened here. And if you see one set, that is somewhere here, this place one, so you will see a pre-basin crater. You can see there is one more crater which has been formed maybe due to ejecta or whatever. Then this is a 2 near the other ring. So you will see the radial textured basin ejecta, you can see here, and then 3. So this is a place say. So this is a post-basin crater, they say. Okay, and then 4 is here. So you can see here also the lava flows are there and dark mantle deposits you can see, and then 5 and 6 is here. You can see this type of, this one. So this is what they call as the multi-ringed basin itself, okay, the Oriental Basin. And here is a famous basin that is that, that Jupiter's, the satellite, that is what we call as Callisto. So this is what they call as Valhalla Basin actually, almost I think 4,000 kilometer diameter. If you see here, so many rings, you can identify from this images itself, okay. So fine. So I will stop here. We will continue in our next class. So if there are any questions, we can ask me, and we will continue in our next class about our this one.